Welcome back to the Deep Dive. Today we are cracking open the architectural blueprints for some of the most advanced systems being built right now.
Yeah, we've been looking at a stack of sources detailing everything from AI personalization frameworks to, scalable cloud architecture and modern
Yeah,
DevOps.
and our mission today is pretty simple. We want to extract the absolute non-negotiable architectural principles, the things you need for speed, resilience, and that real-time user adaptation in 2025. This isn't just about making an app work. It's about making it truly smart.
It really is the whole mandate for what we call a smart application has shifted.
How so?
Well, you can't just build an application that, performs a transaction anymore. The expectation now is that the system achieves real-time prediction. It has to adapt.
Right, making decisions on the fly.
Exactly. And the commercial payoff for getting this right is huge. Our sources are showing that effective AI-powered personalization can drive a significant 10 to 15% lift in revenue.
A 10 to 15% revenue lift. Okay, so that's the strategic justification for every line of code we're about to talk about.
Yeah.
But how? How exactly is AI generating that percentage? Is it dynamic pricing? Is it conversion?
It's all three, but the real power is in the granularity. It's moving away from a simple if-and rule, like if you bought this, you probably like that.
Sure, the old way.
Right. This is about predicting true intent. The lift comes from optimizing the entire user journey, serving the right recommendation at the exact moment of hesitation,
Okay.
optimizing the checkout, and showing the right individualized price to maximize conversion without, killing your margin.
So that real-time dynamism, that speed,
Yeah.
it forces this tension between traditional stability and also new flexibility. Okay, let's unpack this. We have to start at the core, right? The AI personalization engine itself.
Mm-hmm.
And when we talk about AI personalization now, we're not talking about those old rigid rules. We're talking about systems that predict user intent based on these complex, sometimes really subtle patterns.
Totally. The AI is watching everything. The clicks, the session timing, scroll velocity, even those weird hesitation points where a user just pauses their mouse on a product but doesn't actually click.
All of that is data.
All of it feeds the prediction. But that prediction is only as good as its fuel. The foundational requirement for any smart app is a clean, unified user profile.
Right.
And this profile has to blend four key things. Behavioral data, so clicks, feature usage, then contextual data device, location, demographics, and of course, purchase history.
And if that data quality is poor,
Your personalization efforts fail immediately. The models will be trained on garbage.
garbage in, garbage out.
Yeah.
So data quality is the absolute prerequisite. Now, supporting that real-time, high-quality data flow, that forces a huge architectural decision right away. Historically, we built monolithic applications.
That single massive code base.
Yeah, complex to update.
And that single code base had to scale entirely when just one part was stressed. I mean, think of it like a giant cargo ship. If you need to fix a light bulb in the cabin, you have to dry dock the whole vessel.
Right.
If you need more capacity, you have to build a bigger ship. It just scales vertically, getting bigger and slower and, frankly, riskier.
Okay, as a CTO, the risk reduction here sounds huge. What's the single biggest operational headache that microservices solve compared to that monolith?
Oh, debugging and deployment friction, for sure. With a monolith, a small bug fix meant you had to recompile and redeploy the entire enormous system. It could take hours.
Yeah, and it was terrifying.
Absolutely. With microservices, they're small, independent, single-function components. If your recommendation engine has a bug, you deploy only that tiny service in minutes.
Okay, here's where it gets really interesting operationally for you, the listener. That independence doesn't just mean faster bug identification or code reuse.
No.
It means dramatically reduced risk. A failure in one microservice, say your image optimization service goes down, it doesn't trigger a catastrophic failure across the whole system.
It's localized,
Yeah.
and that's structural decoupling. That's step one. But step two, getting to true resilience, means we have to change how these services talk to each other.
No.
If service A calls service B and just waits for a response, they're still coupled. If B slows down, A slows down. That's synchronous communication, and it creates these massive bottlenecks.
So if synchronous is a phone call where everyone waits for an answer, what's the alternative?
The alternative is moving to event-driven architecture, or EDA. Think of it like a mailroom instead of a phone call.
Okay.
When service A, say, the user clicks add to cart, does something, it doesn't call service B directly, it just publishes an event, a notification to a stream. It's like putting a memo on a central bulletin board.
And other services just check the board.
Any other interested service inventory, recommendations, loyalty points, they can subscribe to that event and act on it independently. No one is waiting on anyone else.
That is a massive shift in mindset. You're prioritizing loose coupling over getting that immediate confirmation. But if EDA is so resilient, what's the big complexity it introduces?
Debugging. It's easy to trace a phone call from A to B. But in EDA, tracing the path of an event through 5 different microservices that all react asynchronously, that can be incredibly difficult. You often need specialized tooling.
That's the trade-off.
It's the trade-off for resilience. But that resilience is vital for the AI engine. EDA enables this critical function called training inference separation.
What's that?
AI model training it's super high cost, resource intensive, massive computation. We need to run those pipelines asynchronously. With EDA, we prevent those heavy training pipelines from adding any latency to the user-facing microservices that are trying to serve real-time predictions.
That makes perfect sense. The user can't wait for the AI model to learn something new. Their prediction has to be instant, even if the model is doing some massive quarterly update in the background.
Exactly.
So speed is paramount for that inference. What about the experience the user actually sees, the front-end stack? We hear a lot about MERN or MEVN, but the modern strategic recommendation is the hybrid stack.
The hybrid stack is essential for balancing that speed and dynamism. It uses the performance benefits of what's called Jamstack.
Okay.
Jamstack pre-renders static sites and then serves them over a content delivery network. So it's high security, low hosting cost.
And lightning fast, because you're just serving static files from all over the globe.
Precisely. But that's not enough for a smart app that needs personalization. So the best approach is hybrid. You use Jamstack for static self-marketing pages, generic product listings, and then you leverage serverless functions, or phase, for the dynamic, personalized parts.
The individualized recommendation carousel or the personalized pricing.
Those are driven by phase or microservices that are just seamlessly injected into that static shell.
So all that back-end complexity is hidden behind this super fast wrapper. If the backend is that complex and distributed, the API becomes the client's single gateway to everything. We have talked API design, specifically REST versus GraphQL.
Right. REST is the simple standard. It's great because it uses built-in HTTP caching, which is fast, but its major problem, especially today, is overfetching.
Overfetching.
Yeah. You might request a user object and get this massive data payload address history, purchase logs, every preference, when all you really needed for that UI screen was their first name.
That wasted network traffic sounds especially painful on mobile.
It is, and that's where GraphQL reigns supreme for the client-facing layer. GraphQL minimizes that overhead because the client specifies exactly the data it needs in a single request. It gets rid of overfetching and underfetching.
Which is critical for mobile or low bandwidth areas.
Absolutely. You only pay the network cost for the data you actually asked for.
So what's the strategy? Go all in on GraphQL.
We recommend a hybrid API strategy. Use GraphQL as that single public-facing API gateway for your front end. It acts as an orchestration layer. Internally, though, those services can use simpler REST APIs or those EDA event streams to talk to each other.
Wait a second. The flexibility we just praised GraphQL for, the client asking for whatever it wants, that sounds like its biggest security vulnerability, too.
It absolutely is. Because a client can request arbitrarily complex data in one query. A malicious actor could just overwhelm your backend. They could request 10 nested levels of data and crash your database.
So you have to implement specific controls. What are they?
First, query depth limiting. You just set a maximum nesting level, say 10 levels deep, and you reject anything that goes beyond that.
Simple enough.
Second, and this is smarter, is query cost analysis. Instead of just rate limiting the number of queries, you rate limit the user based on how many resources the query consumes. A simple query is cheap. A deep nested query is expensive.
That is smart. You're protecting resources based on effort, not just volume. And since we're talking about all these distributed, stateless microservices and functions, maintaining a user session across them sounds like a nightmare.
You're right. That's why the stateless nature of FES and microservices is best suited for JSON Web Tokens, or JWTs. Unlike old session cookies that require every service to check a central cache, a huge bottleneck, JWTs carry all the authentication data in a self-contained, signed token. The service can verify it locally without any external calls.
Which simplifies everything and helps it scale.
Exactly. Let's pivot to the data layer. Because we're dealing with traditional transactions and these massive real-time behavioral streams, we need what's called polyglot persistence.
Meaning different databases for different jobs. This isn't optional.
Not for a smart app, no.
Yeah.
You can't use one database for everything anymore. You'll just sacrifice either consistency or speed, probably both.
So where does classic SQL fit in?
SQL databases, relational ones, are still mandatory for your transactional data user accounts, inventory, payments. That's because you need ACD properties. You need that strict consistency. You can't have a payment go through without debiting the inventory.
But that strict consistency comes at the cost of the speed and volume needed for the AI's fuel.
Right. So for the high throughput, massive data volumes, unstructured data like event streams, clicks, all the stuff for the ML model, we use NoSQL databases. They're built for flexibility and horizontal scaling. They can handle that fire hose of data.
Okay, now for the compute engine. Serverless functions, or FAS. This is what serves the actual prediction. The big concern used to be cold start latency, right?
Yeah, the time it takes for an instance to spin up from zero, that used to keep FAS out of real-time scenarios. But that latency concern has been aggressively mitigated by the providers.
So it's viable now.
It's the default for modern event-driven inference, which raises an important question. Which provider do you choose? The differences are pretty dramatic.
Okay, let's start with the market leader, AWS Lambda. What's their killer feature for cold starts?
AWS's key innovation is SnapStart. If you're running Java, cold starts could historically take 5 to 10 seconds. SnapStart reduces that to sub 200 milliseconds by taking a snapshot of the initialized environment. It's a lifesaver for big enterprise Java migrations. Plus, their ARM Graviton 2 architecture offers about a 20% cost saving.
So if you're a Java shop and need cost efficiency, AWS is a clear winner. What about Google Cloud Functions?
GCP, especially the second gen, is all about concurrency. While an AWS function usually handles one request at a time, GCP can handle a default of 80 concurrent requests per instance. 80. This can lead to a 40% cost reduction versus their first gen, and you need 70% fewer instances to handle the same load.
So concurrency and raw cost reduction are GCP's game. What about Azure Functions?
Azure is the ideal choice for Microsoft-centric organizations. If your team is already deep in .NET or PowerShell, it's a natural fit. Their unique feature is durable functions, which are excellent for orchestrating stateful, long-running workflows entirely with serverless tech.
So what does this all mean for you, the listener, building this app?
Well, the strategic choices. First, commit to the platform where your team already has deep expertise. But then, prioritize the specific features that solve your biggest bottleneck: Java latency, AWS, concurrency and cost, GCP.
That makes sense. Okay, finally we have to talk operations. Managing this complex distributed system, it requires true observability.
Right. Integrated logs, metrics, and traces. Not just simple monitoring that tells you the server is up. You need to know why it's slow.
And the latest revolution there is AI-powered log management.
Absolutely. Traditional monitoring just alerts you when a threshold is crossed. Now, AI analyzes patterns across billions of data points to identify issues proactively before they become critical failures.
So it's predictive.
It is. And when an incident happens, the AI correlates everything: logs, metrics, traces, to pinpoint the root cause. It tells you not just what happened, but why. And that drastically slashes your mean time to resolution.
Which means your choice of an APM tool, your performance management platform, is a critical business decision. And there's some real friction in the market here.
We see a clear financial anti-pattern emerging. Some APM tools, like Datadog, historically base their pricing on things like charges per host restart and extra fees for containers.
Wait, so the core benefit of your architecture, auto-scaling elasticity to save money is financially penalized by your monitoring tool.
Precisely. Every time a new instance spins up, you pay an extra fee. You are penalized for being flexible.
That's a huge conflict of interest.
It is. Platforms like New Relic, which use a more predictable, usage-based pricing focused on data ingestion, are often a better fit. They don't disincentivize that rapid auto-scaling. It's a key financial risk to watch for.
Okay, before we wrap up, one last thing. Safety. In this distributed world, how do you stop changes in one service from silently breaking another?
That requires contract testing, and it has to be embedded right into your CI/CD pipeline.
The contract.
An explicit version-controlled agreement between the services about the data format they exchange. The contract tests enforce that agreement. So if a team upstream changes a data field, the pipeline breaks, and you know immediately you've broken something downstream.
That is the key to achieving agility safely. Okay, so to recap the blueprint for this modern smart app, We start with microservices and event-driven architecture for resilience.
Hmm.
We front it with a low-latency GraphQL gateway. We use polyglot persistence for data and serverless functions for compute. And the common denominator in all of this is a relentless optimization for low latency and high throughput.
All driven by that 10 to 15% revenue lift that personalization provides.
Exactly.
And here's the final provocative thought for you to consider. The core asset of a smart app isn't the database. It's the intelligence. It's the ML model itself.
Okay.
So your architectural and operational efforts have to go beyond just system health. The future of operations requires leveraging that AI-powered observability to actively monitor the health and performance of the ML models themselves.
You mean watching for things like data drift or the model getting stale?
Exactly. Detecting subtle issues like data drift or model degradation before they impact the quality of the user's personalization, that's where the real competitive edge truly lies.